All right.
In Glenview, high winds took down a power line, trapping a woman inside her car. Police did not know if the wire was live, so they ordered the woman to stay inside the car to avoid
This time,
contact with the ground.
question is this. Notice that the car is
And then they
part of the circuit.
shut down the entire
So the entire car is electrified.
intersection. The driver was trapped for nearly 2 hours until ComEd crews showed
And you know why she's safe while she's on the inside.
I called for the fire.
My question is,
the wire. Police
that I've been
did not know if the
you can touch all the metal on the inside. All right, you're going to be 100% safe. And you guys understand the reason now. Of course, guys, that's always the task question. So I also said she can touch the metal on the outside. All right, so window is open. She can just reach out and touch the metal on the outside. She's still going to be fine. So the question is why? We kind of discussed that yesterday a little bit. And does anybody know or understand why you should be okay touching the metal on the outside? You can touch the metal on the outside. As long as you're sitting on the inside, you can touch the outside of the metal, outside of the car. You're still not going to get electrocuted. Caleb. I mean, if you have any theory. Say it again, Caleb.
Because you're part of the circuit.
All right. When you guys say that, I understand that that's the sentence, but what does it mean? I'm looking for some kind of understanding. You're part of a circuit, so is the guy on the electric chair. He's also part of the circuit, but he's not getting killed. I mean, that guy is getting killed, but she's not getting killed. So the question is, what does it mean that you're not part of the circuit? She is part of the circuit. Yet she's perfectly fine. I mean, she can touch.
Oh, well, I think it's because all the electrons on the metal, so it's a conductor, so they're able to move freely, and she's on the inside where there's an opposite charge.
All right, Caleb, I'm going to give you 5 points for that one. All right, does anybody else have a theory regarding that? Do you want
I think she'll be okay because there's no current path, so like the entire car is charged, and like there's no way for it to discharge through her if she's on the inside of the car. Okay, but if she like steps out of the car, I think she gets zapped because her body would form a path for the charge to drain to the ground.
All right, so Nathan, I'm going to ask you, why is it that the current is not going through her body?
When she's in the car?
When she's in the car, yeah, I think that's what...
I think it's because it would have to, since the whole car is charged from the electric wire.
I mean, just imagine that the current, the electricity is just running through the car, right?
Right.
This is not a static case. The charges are moving through the car, through the surface of the car, let's say, all right? So why is it that when she touches the outside, she's not getting electrocuted?
Maybe because even though the charge is moving, it moves preferentially through the metal because it's a better conductor.
Okay, that's not a bad answer. I'm going to give you 10 points for that one. What I'm looking for is a little bit more than what you guys came up with. And I'm looking for some a little bit deeper than that. Did you guys notice that the spark happened at a certain distance? It's about an inch or less. All right, why does the distance matter regarding the spark? When the first thing it does, he charges up the body. His body becomes polarized. Then end up getting this spark right there, right there. All right, so that's about an inch or less. All right, why does the spark happen?
Because
the distance that it does. Nathan, go ahead.
Because air has like a breakdown voltage, so you need a certain amount of potential difference between the guy's finger, the kid's finger, and this guy before it'll spark. And if you're too far away, the voltage potential is enough. Once you get to that same the right distance, it'll jump the gap, something like that.
Okay, so the air has a certain discharge potential voltage, which is what,
yeah, like I think it's called like a breakdown voltage or something like that.
I think that's what it's called. What is it, like 3 million?
I don't know.
Per coulomb. That's the strength of the electric field, according to the books. Okay, so what do you mean by voltage?
It's like the difference in potential or the difference in charge between 2 points. So, like if he's got a super big positive charge and then there's like a negative charge on the other side, it's kind of like the difference between the two.
Okay, I'm going to give you 10 more points for the explanation that you provided. At least you have some kind of a theory in your mind. So that's interesting.
Yeah, I think the difference, but then it's how much it wants to flow because of that difference, isn't it?
Well, Matthew, I like that explanation as well. All right, I'm going to give you 5 points. So it's the tendency to flow with discharge, right? You got two oppositely charged regions. So if you could measure the tendency of discharge, you could probably call that voltage or potential. I just made that up based on what you guys said. And it kind of makes sense to me at this point. All right, so we'll come up with a little bit more formal definition that I want you guys to remember. So if that's the case, high ground versus the low ground, which one is more likely to be struck by lightning? You kind of know the answer, right? High ground is more likely to be struck by lightning. So how do we come up with that idea? All right, so that's question number one. Question number two, why the hell is that idea not 100% correct? All right, because if high ground is more likely to be struck by lightning, high ground should be struck by lightning 100% of the time, which means that the tall structures are the ones should be getting hit by lightning 100% of the time, yet it doesn't happen 100% of the time. So why does the physics fail, or does it? We'll find out.
Bob and I are here to tell you about something that has us very excited. NEC's Parabola range of televisions. They've got a 3-year warranty, which we think is fantastic. They come from the same people who have sold over 1 million Australian-made colour televisions. Superb sound comes from the surround sound speaker system, but...
All right, so it's a commercial from Australia, and they're obviously trying to sell you high-definition TVs. Cute. If you had to rate the quality of this commercial out of a 10-point scale, most of you guys would rate it as 1 or possibly 2, right? It's not the sort of high-quality, high-energy commercials that we're used to from the United States, and that's part of the reason why the United States is such a great place to live in, right? Because of the quality of the commercials.
The best feature of NEC's Parabola is its...
Oh shit! All of a sudden, this goes from 1 to 10.
Lifelike picture.
It's called misdirected. You guys didn't notice that the guy in the back
Bob and I are here to tell you about
was not there. It's just a high-definition TV, and the quality of the TV is so good that you can't tell.
something that has us very excited.
This guy is going to be as boring as possible, and this guy's going to be as bored as possible.
NEC's Parabola range of televisions. They've got a 3-year warranty, which we think is fantastic. They come from the same people who have sold over 1 million Australian-made colour televisions. Superb sound comes from the surround sound speaker system, but the best feature of NEC's Parabola is its lifelike picture.
I got news for you guys. These high-definition TVs have been around for about 20 years. Most of you guys are about 20 or less, so it's not a big deal. All right, so 20 years ago, I was working on my PhD in nuclear physics in Virginia, Norfolk, Virginia, and decided to come to Chicago because I got bored just working on the dissertation. I figured that I could finish it up on my own, and I kind of enjoyed the teaching gig. It was fun. So I got a job at an art school. They were looking for someone who could teach physics conceptually and visually, and I thought I was the right person for that job, and they believed me. As it so happens, I was wrong. All right, guys, teaching physics to art students, not mathematically. Are you freaking kidding? All right, only in the movies is something that you could do. In reality, I had no idea how to do it. Next thing you know, I'm wasting 20, 30, 40, 50 hours a week preparing these 5-hour lectures. And I had no time to work on my dissertation, no time whatsoever. And the lectures were just shit. I was swimming in shit. I was making $30,000 a year, barely enough money to pay my rent. And then I decided that I should probably go get a real job, do physics research, get paid for it, 40 hours a week, and then just finish up the dissertation at night. All right, so I started looking around. I got lucky. A company named Zenith was looking for a physicist, a researcher. Those of you guys who don't know, Zenith was a huge name at the time. All right, it was as big as Microsoft. So this is a Chicago-based company. They would used to make TVs and then computer monitors. So they were interested, so they called me up. So I went to the interview. The first thing I did, I talked to the HR, human resources. And so the only thing I wanted to know was, hey, what's the salary like? And then she said, oh, it's $120,000 here. That's the starting salary. $120,000, guys. That's 4 times the money that I was making. On top of that, the nice thing about it is you work 40 hours a week. It's solid. That's it. I said, great. So what is it that I need to do for that? So she said, well, you need to go to the physics department. They'll explain it to you. So I figured that they had a huge physics department. So this is a big company. So I went downstairs, and there's a big room, and there's a small desk, and there's a guy sitting across. So we sat on, and then we've had a little bit of a small talk. The first question he asked, do you know what HD TV is? Never heard of it. I know what TV is. I figured that that's television. So I said, what does HD stand for? The guy says it's high definition. I'm looking at it. So what does it mean? He said the TV quality, image quality is just like, it's so good that it's better than real life. And I thought it was kidding at first. And now you guys, it's digital quality. If you're watching football, check to see if you can actually see the actual grass on the field while you're watching football. Just go near the TV. Image quality is so sharp that it's actually better than life. Imagine that. So I said, oh, that sounds like a great idea, man. So that's what I was thinking. He said, so, and then he goes, well, do you know much about the TV? Do you know much about the way the TVs work? I say, yeah, just give me a remote. I'll show you. He said, do you understand the electronics of it? At the time, I spent about a year trying to get my master's in electrical engineering before returning to physics. I said, not only do I know how the electronics of it work, I said, I could build one if I wanted to. He said, no, we don't need you as an engineer. He said, we need you as a physicist because we have a huge problem. I said, what is the problem? So this guy starts to describe the problem. And the problem that they had was kind of weird. It's interesting. All right, so the description of the problem, this is the stuff that we will build upon because this thing is going to keep coming up. These are known as cathode ray tubes. This is the way the TVs used to work 20 years ago. Technology changed completely. All right. So they used to have this region, which engineers refer to as an electron gun because the engineers are cowboys. In physics, we say these are capacitors. One region is going to be negative charge, the other region is going to be positive charge. And then you have this filament, and then you would heat it up, so which means that the electrons would become ionized. And then you would have this stream of electrons, which is known as the electron beam, moving towards the hole in the metal. All right, so in essence, you're shooting electrons through that hole. This is the reason why this is known as an electron gun. All right, and so he's describing it. He said, in order to generate high-quality images, so you generate this electron beam, and then you have the screen here. And then what you do is by using electromagnets, you take the electron beam, and then you scan it onto the screen. onto this screen. Regular TVs, a couple hundred times per second. High definition TVs, you do a couple of thousand times per second. Now, for you to be able to get this electron beam onto the screen a couple of thousand times per second, the strength of the electric field to accelerate these electrons have to be extremely, extremely high. All right. So the strength of the electric field needs to be high. So what's happening is the electric field acting on these charges will cause a force, and the force is going to cause a tremendous amount of acceleration. Got it? And then so you grab the beam and then just scan it onto the screen. All right. And so I said, so what's the problem? The problem, he said, the prototypes that they had a lifetime of about 6 months, and they were spending about $10,000 for each prototype. And within the life of a TV, which is about 6 months, it would generate a spark within this gap, within the gap of a capacitor, and this would completely fry the electrons. So you get your zap. That's it. It would zap the shit out of the electrons. All right. So he looks at me. I'm looking back at him. I said, so what do you want me to do? So a couple of things about this is relevant. All right. What's relevant about this is this zap. All right. So you end up getting this zap. What's causing it? Why is it that I knew that this didn't have much to do with physics at that point? Because the stuff that you guys are looking at is the same stuff that we've been struggling with regarding lightning. It's identical to lightning. Okay, the sparks in the laboratory, remember, this is what Ben Franklin was trying to figure out. It's exactly the same as the lightning pop. All right, the stuff that we don't understand about lightning is exactly the same stuff that we don't understand regarding what generates the spark over here. All right, and that's the problem that they were trying to solve. And just sitting there for about 5 minutes, I knew there was no way we were going to be able to solve this problem using physics. I knew that. The 3 ideas that I had, they were really, really simplistic. And then as soon as I knew that was not going to work, this was no longer a physics problem. All right, so another thing that we need to talk about is the high voltage magazines. Strength of the electric field is what I'm talking about. High voltage magazines. What's the meaning of voltage? And how does the voltage difference or the potential difference cause the spark? And why does the distance matter? And this is the distance that you have. All right, so these are the things that we will discuss today. All right. All right, take a look at this, the positive charge. You bring a positive charge near a positive charge, what's going to happen to it? As soon as you let it go, it's just going to accelerate in the opposite direction, right? Fly. All right, so when you bring a positive charge near a positive charge, there's going to be a repulsive force, right? And so what happens when you let it go, the charge is going to accelerate away. Okay. So when you do work against gravity by lifting something up, what happens to the object that you're lifting? You energize it, right? All right, so when you lift something up, when you do work against gravity, the amount of work that you do against gravity goes into the energy of that object, right? So it becomes stored in that object. So the amount of work done against the conservative force is going to become stored in that object as its potential or potential energy, right? So when you bring a positive charge near a positive charge, you have to do work against the electrostatic repulsion. You have to do work against the electrostatic force. The amount of work that you do against the electrostatic force is going to go into the potential energy of the charge. It's the same as the gravity analogy. So when I lift this key up, notice that I'm energizing it, and when I let it go, the conservative force is going to take over, right? So in this case, it's gravity. When you let it go, what does gravity do? It takes the potential energy, the stored energy of the subject, and turns into kinetic energy. Likewise, whenever you bring a positive charge near another positive charge, the amount of work that you do is going to go into the potential energy of the positive charge, and when you let this positive charge go, its potential energy is going to quickly get converted into the kinetic energy of that charge. So what does that tell you about the electrostatic force? Electrostatic force is exactly the same as gravitational force, in that sense that it is a conservative force field. All right, so conservative force field. So when you have a conservative force field, what happens? The total mechanical energy will become